Have you ever looked up at the night sky and wondered, how did it all begin? Not just the stars and galaxies, but us. How did a barren, lifeless rock, our Earth, give rise to the incredible diversity of life we see today? This is the greatest detective story of all time, a journey back 4.5 billion years to uncover the very origins of life. And today, we're going to crack the case. Our story starts in a chaotic young solar system. Imagine a swirling disk of gas and dust around our newborn sun. Through countless collisions and gravitational pulls, tiny particles clumped together, growing larger and larger until our planet was born. For millions of years, Earth was a hellish landscape, a molten ball bombarded by asteroids, with a toxic atmosphere and no liquid water. It was the most inhospitable place you could imagine. So how did we get from that to this? The first clue lies in a groundbreaking experiment from 1952. Picture a young scientist named Stanley Miller working in a lab with his mentor, Harold Urey. They wanted to simulate the conditions of early Earth. They filled a glass flask with water to represent the ancient oceans, and a mix of gases like methane, ammonia, and hydrogen to mimic the primitive atmosphere. Then they zapped it with sparks, simulating lightning storms that would have raged across the planet. What happened next was astonishing. After just 1 week, the clear water turned into a murky, reddish-brown soup. When they analyzed it, they found something incredible. Amino acids. These are the fundamental building blocks of proteins, the molecules that build our bodies, run our cells, and make life possible. The Miller-Urey experiment proved that from simple, non-living chemicals and a bit of energy, the very ingredients for life could form spontaneously. It was the first piece of the puzzle, showing that the path from non-life to life wasn't as impossible as it seemed. The raw materials were right here from the start, but having the ingredients isn't enough. You need a recipe, a way to organize those building blocks into something complex and functional. This is where our story takes a turn, diving deep into the microscopic world of molecules. For a long time, scientists faced a classic chicken and egg problem. To have life, you need DNA to store the instructions, and you need proteins to carry out those instructions. But you need proteins to build DNA, and you need DNA to make proteins. So which came first? The answer, many scientists now believe, is neither. The star of the show was a different molecule entirely: RNA. RNA, or ribonucleic acid, is like DNA's lesser-known cousin, but it's a true multitasker. Like DNA, it can store genetic information, but unlike DNA, it can also fold itself into complex shapes, much like a protein, and act as an enzyme to speed up chemical reactions. This dual ability is what makes it the perfect candidate for the first self-replicating molecule. Scientists call this the RNA world hypothesis. Imagine a primordial soup brimming with the amino acids and other chemicals from Miller-Urey type processes. In this soup, simple RNA molecules were forming. By pure chance, some of these RNA strands developed a remarkable ability. They could make copies of themselves. This was the watershed moment. For the first time, there was a molecule that could replicate and pass on its information. It was the birth of heredity, the dawn of evolution. These early RNA replicators weren't perfect. Errors or mutations would occur during copying. Most of these errors were useless, but every now and then, a mutation would make an RNA molecule slightly better at replicating itself. It might be more stable or faster at copying. These superior versions would naturally make more copies, dominating the primordial soup. It was natural selection in its most basic form, acting on simple molecules. Over millions of years, these RNA molecules would have become more and more complex, creating a dynamic ecosystem of competing and cooperating strands. They were the first genetic code, nature's first attempt at writing the book of life. But RNA had its limitations. It's not as stable as DNA for long-term information storage, and proteins are far better at performing the complex chemistry of life. So evolution found a better way. The next evolutionary leap was the development of proteins. The RNA world likely evolved the ability to string together amino acids, creating the first simple proteins. These new molecules were specialists, far more efficient at building structures and catalyzing reactions than RNA ever could be. Eventually, the role of information storage was outsourced to a more stable, durable molecule, DNA. With DNA as the secure blueprint, RNA as the messenger, and proteins as the workforce, the modern system of life was born. This division of labor was so successful that it has been conserved in every living thing on Earth, from a bacterium to a blue whale. So we have self-replicating molecules. But we're still not at what we would call a cell. The final crucial step was encapsulation. Life needs a boundary, a way to separate its internal chemistry from the chaotic outside world. Think of it like a house. You need walls to protect you from the elements. For the first cells, these walls were likely simple membranes made of fatty molecules called lipids. In water, these lipids have a neat property. They spontaneously form tiny bubbles or vesicles. We call these protocells. If a self-replicating RNA molecule and its associated proteins happen to get trapped inside one of these bubbles, it would have a huge advantage. Inside this private little compartment, all the necessary chemicals would be concentrated, making reactions much faster and more efficient. The membrane would protect the delicate genetic material from being washed away. This was the first cell, a simple bag of chemicals, but it was a self-contained, self-replicating unit. It was alive. From this single common ancestor, all life on Earth diverged. For billions of years, life remained simple, single-celled organisms floating in the ancient oceans. But slowly, steadily, evolution worked its magic. Cells learned to harness the sun's energy through photosynthesis, pumping our atmosphere full of oxygen. They learned to cooperate, forming complex multicellular organisms. This set the stage for the explosion of life that would eventually lead to fungi, plants, and animals, including, after billions of years of twists and turns, us. Every cell in your body carries the legacy of that 4 billion year journey. Your DNA contains a genetic code that can be traced back to the RNA world. The proteins that power your muscles are built from the same 20 amino acids that formed in experiments like Stanley Miller's OSS. The story of our origin is written not just in the stars, but inside of us. It's a story of cosmic chaos, chemical serendipity, and the relentless power of evolution. So the next time you look at your own hand, or a tree, or any living thing, remember the incredible, improbable journey it took to get here. From stardust to simple molecules, from replicating RNA to the first cell, and finally, to the magnificent complexity of life we see all around us. It's the greatest story ever told, and it's our story. Thanks for joining me on this incredible journey through time. If you're fascinated by the big questions of science, make sure to subscribe and hit that bell so you don't miss our next adventure. Let us know in the comments what other mysteries of the universe you want us to explore. Until next time, stay curious. Ever wonder where it all began? Let's rewind the clock way back. About 3.5 billion years ago, in the primordial soup of a young Earth, the first cells sparked into existence. These weren't complex creatures, but tiny, tough prokaryotes. They didn't just survive, they thrived in extreme conditions, and you can still see their legacy today in ancient rock formations in Australia called stromatolites. Then came a game changer, cyanobacteria. These microscopic powerhouses figured out photosynthesis, and in doing so, they started pumping a new gas into the atmosphere, oxygen. This great oxygenation event was catastrophic for early life, but it set the stage for a world like ours. The next leap was an incredible act of teamwork. One cell engulfed another, but instead of digesting it, they formed a partnership. This is how our cells got mitochondria, their power plants. It's the birth of the complex eukaryotic cell, the ancestor of all plants and animals. From these simple beginnings to the person you are today, this epic story is written in your DNA. We are the legacy of life's incredible journey. Thanks for watching, and don't forget to subscribe for more amazing stories from our past.